Hey everyone, we are swimming in data every single day, right? Polls, forecasts, studies, they're everywhere. But how much can we really trust any single number? Well, today we're going to dig into a really powerful statistical tool that helps us answer that exact question.
Okay, so here's the big challenge we always face with data. We almost always have just a small piece of the puzzle, what we call a sample. But what we really want is to understand the whole picture. So the massive question is, how do we know if our one little sample is even close to telling the truth?
Think about it like this. You brew a brand new pot of coffee. You take one sip, and it is absolutely perfect. But hang on, what if you just happen to scoop up the one little bit where all the sugar settled? That one single sip might not represent the whole pot at all. That, my friends, is sample uncertainty. And it's exactly the kind of problem we're going to solve today.
Fortunately for all of us, some very clever statisticians came up with an amazing technique to handle this. It's called bootstrapping. And yeah, it's kind of like pulling yourself up by your own bootstraps, but, for statistics. It's a way to build confidence out of the data you already have.
So the big idea behind bootstrapping is, well, it's surprisingly simple but really genius. It lets you take that one sip of coffee, your single sample, and use it to simulate taking thousands and thousands of different sips. This gives you a much better feel for the entire pot, and you don't even have to brew another one. All right, let's get the formal definition on the table. Bootstrapping is a statistical technique for estimating a population statistic from a sample by generating many random samples from the original sample. So what does that really mean? Well, we're essentially treating our one sample like it's the entire universe. Then we create thousands of new, fake samples by just drawing from that original one over and over again. And the key is we do it with replacement, meaning every time we pick a data point, we put it back in before picking the next one. This resampling is what lets us see all the possible ways things could have played out.
Okay, so we've run our simulation, we've got thousands of new bootstrap samples, and we've calculated our statistic. Let's say it's the average for every single one of them. Now we're sitting on this huge list of possible averages. What do we do with it? Well, there are two main ways to use this list to measure our uncertainty.
First up, we've got the bootstrap percentile method. Imagine all those thousands of coffee sweetness averages we just calculated. This method is pretty straightforward. It just lines them all up, from least sweet to most sweet, and then it lops off the bottom 2.5% and the top 2.5%. What's left in the middle, that 95% chunk, is our range. It gives us a direct look at the most likely outcomes.
The second method is the bootstrap standard error. Now this one's a little different. Instead of spitting out a range, it looks at all our simulated sweetness averages and calculates how much they typically wobble around the original value. It boils all that variation down to a single number that tells us, on average, how spread out our results are. A small number means our estimate is rock solid. A big number means it's kind of all over the place.
So we have these two different tools. One gives us a range using percentiles, and the other gives us the single wobble number using standard error. Let's put them head to head so we can really get what the practical difference is.
Here's probably the clearest way to think about it. The bootstrap percentile gives you a range. It basically hands you a finished product. It says, we are pretty confident the true answer lives somewhere in here. On the other hand, the bootstrap standard error gives you a measure. It's more like the raw materials. It's that crucial building block, that number telling you how wobbly your data is, that you then have to use to construct the final answer.
Let's just walk through this table because it really nails the difference. The percentile method, it tells you a range of likely values. You use it to create a confidence interval directly. And what do you get? Two numbers, a lower and an upper bound. Done. Now, the standard error just tells you how much your estimate wobbles. It's a building block for a confidence interval. And what do you get? Just one single number. So one gives you the final headline, the other gives you a key piece of the math behind it.
So after all this, why does it matter? It matters because being able to quantify uncertainty is what separates a wild guess from an actual informed statement. It's about getting to move past saying, I think this is the answer, and getting to say, here is the range where the answer most likely is, and here's exactly how confident I am about that.
And this is the real magic. Instead of making this really definitive and, let's be honest, probably wrong statement like, the answer is exactly 5, bootstrapping allows us to say something way more powerful and way more honest. Based on our data, the true answer is very likely somewhere between 4 and 6. That range isn't a sign of weakness, it's a sign of real statistical rigor.
And that brings us to this key quote from our source material that just wraps it all up so nicely.
Both bootstrap percentile and bootstrap standard error provide ways to quantify the uncertainty of an estimate, but they do so in different ways. One gives you that direct, ready-to-use range. The other gives you a precise measure of the variation. Both are just incredibly useful tools for really understanding our data. So the next time you see a poll or a study or any statistic that's just presented as a single, certain number, I hope this makes you stop and think. And I hope it empowers you to ask the single most important follow-up question there is. Okay, but what's the uncertainty? Thanks so much for joining us.